Hello everyone, I'm Krzysztof, and as we said, I am Scala specialist at Virtuslab. And today, I want to take you from the world of monads, from the world of streams, into this dirty world of tooling. And to be concrete here, I want to talk about incremental compiler, and so in the end, how to tame the Scala C, because Scala C is it's slow. Yeah. And the question I got for all of you is, do you think that Scala C itself is incremental compiler? Can you raise your hand if you think that Scala C is incremental compiler? Nice. I expect at least 1 or 2 hands, but like almost none. Oh, there's one, okay. Yes, Scala C is not an incremental compiler. Scala C compiles, well, you ask him to compile. So if you compile all the project, you get like hours wasted or something more. So what incremental compiler actually is for us? So I think the compiler and incremental compiler, sorry, I'm messing this up, is a driver. It's a driver that takes Scala C and feeds it with some subset of sources to compile. Because for small changes, we don't need to compile the whole stack, whole project. Just usually, I don't know, changing one function don't affect like all classes on all Scala sources in our code base. Only few amount of them, like 5%, 10%, or maybe none. So this is what incremental compiler actually is. It just drives the Scala C, so not all the sources need to be recompiled. And another question for you. How many incremental compiler there are for Scala? Like 2? Can you raise your hands? With 2? 3? Okay, 4? More? So I think there is only 2. Maybe there is more. I don't heard about more, but the first one is done in SBT. It is also known as Zinc and used, for example, in Gradle, if you want to use Gradle with Scala. And it's also used in Scala IDE. And the second one, it's created by JetBrains and is present in the IntelliJ. So there is like only 2 options there. For maybe there is more, but I don't heard. And anyone using different incremental compiler? Okay, so yeah, as I expected, just 2. Yes, and today I want to explain and go into the SBT one, because IntelliJ is not that fun, because it's not written in Scala, for example. It don't use Scala C. And most of us probably use SBT. Who are using IntelliJ incremental compiler for daily basis? A few of us. It's something. Okay. So all code that we will explain later, shown later, it's not actual SBT code. This is a code that I created just to show you, because incremental compiler, it is connected to compiler, so everybody assumes it's not that easy, and it is true. It's hairy, it's complicated, and I think most of the code examples I want to show you don't fit in this kind of slide, or it have to be like this kind of, the font will be this small, so I don't want to do that. Actual code can be found on GitHub, as you probably can imagine, especially the compiler. SBT structure is not so readable from the start, but you get used to that in the end. So our compiler, I mean incremental compiler, because it's not actual compiler, it's basically can be represented some kind of this, like this function. So at first, we need to see what is initially changed. Then, to be doing it in loop, we just need to look what is the APIs of the files that we are planned to compile in that step, compile the classes and find the new APIs, find the difference between those APIs, and find all classes that can be affected by those APIs, and compile it again. It seems trivial, but it's not in the end. And question that probably comes to your mind is, why do we need this recursion? So the answer is, we don't need that recursion, but then we have to re-implement Scala C itself. So if we can like look at the changes in sources and say, okay, this will change this type to this thing, so we don't need to compile this, only this and this file. But this means we have to re-implement Scala compiler. And we don't want to do that because it's complicated, and we just want to be more focused on finding the dependencies between sources, between classes, between methods, and stuff like that. That is why we need the compiler. And Scala compiler, Scala itself, we don't need to have a type provided in Scala. So any change, like in anywhere, can change multiple return types, multiple APIs, and I don't want to mention implicits and some more complicated stuff. That is why we need this recursion. Okay, so right now we know why we need recursion, so let's see what is this initial change sources, because this is like entry point to our application. So as you can imagine, the second part is just find all sources that was actually changed. And this is done checking the hashes of the actual source files. And this is really trivial. But why do we need this first part? I mean, why do we need to see if, for example, output changed or options changed? And by options, I mean Scala compiler options. The answer is because they will affect all compilation of all the sources. I mean, if the output changed, it probably means that new output is clear. If the options changed for the Scala C, it will recompile differently. So we have to recompile it all again and again. But this is not this. We don't change this kind of stuff really often. So it is not that scary. I will simplify a lot of stuff because right here, I don't care about change libraries. I don't care about if some of binaries in the auto compilation is removed. I take off this part from actual compiler, just not to like spend 2 hours here and talking about something that might be obvious in the end. Sorry, something goes wrong. Okay, so right now we know what was initially changed. So let's go into the compilation, because the previous parts, I mean, storing the APIs, looking at these old APIs, finding what was changed, is pretty trivial in the end, and this is like really implementation detail. It is not the actual algorithm. So how we can find the IPA of the class? There's probably, you can say, you can use Java P or Scala P, but this is not enough for us. We just want to do more, and that is why we want to use what Scala C is using in the bottom. So we want to hook into the Scala C itself. So how to hook into the Scala compiler, how to run our code into the compiler? There are 2 options. First are macros, but macros are limited for class, annotated, or given method. So it will not cover all of the places we want to cover. So the second option, and option that is used in SBT, is compiler plugin. SBT creates a compiler plugin that adds phases to the compilation. Those phases are placed in the end of the compilation. So then all the tree that we have, it's fully typed. All the symbols is present, and so we don't need to type it again. We just have to get the information from that tree. And in the actual code is implemented by, this is a little bit different than this, more hairy. This is like the idea, so we just pass the listener, and in the end we get the information from the listener when the compilation is done. This listener will also store the information about the problems, about the warnings, and the warnings are a little bit tricky. It's really hard to track the warnings in incremental compilation, but this can be another talk for that. So once we when the compilation is finished, we just update our states, return the APIs. So let's go deeper again. So we are inside the listener, and this is taken as some kind of phase in this way, but it actually is implemented as phases. There are 2 phases for that, and they plan to merge it, or this merged already, into the one phase. So it's a little bit faster. And how phase looks like? There's 2 options, more or less. First, you can transform all sources all together, or you can apply your transformation, or in our case, just getting information for each compilation unit at the time. And compilation unit is more or less a source. So what we are doing here, in the first step, we're taking the hashes from the source and store those hashes somewhere. those hash, because right now it's only one hash. There will be more hashes in the future. And then we just traverse the source again and store all the dependencies. And dependency is more or less the source file that, if it's changed, my source file probably can be changed. So this is basically used in my source file. How traverser works? Probably you know how traverser works. If not, this is a really simple idea. If we have a tree of the source code, we override method traverse that is applied for each of the nodes. And if we want to go deeper, we just call super. I don't know if calling for super is right now a good idea. Never mind. And if we don't, just stop the compilation on a given node. And of course, we have to start this computation. So our traverser for hashes, for the APIs, it's really simple. We have to hash all the non-private methods or non-private members, which means we have to hash each non-private method. So we don't care about method body, because it doesn't affect the return type. So if I change the body without returning type, and I got the times from the compiler, I don't need to go into these big details. And of course, we have to hash all the classes, all the types, everything that is non-private. And we stored it in a single hash. Of course, this is old approach. Right now, it's more sophisticated, but I will come to that later. For the beginning, for understanding how it works, I think this is a good start. So right now, we got the single hash for each source file. And the same story comes from the dependencies. But there, we have to go through each of the tree, element of the tree, because we need to grab all sources that we depends on, or the files that we depends on. So we traverse everything, every body, every operation, everything, just to get where is declared and what we need to depend on. And this is basically all. Once we got these dependencies, once we got these APIs, we can do it again until there is no more changed APIs. So it's usually 1 or 2 or 3 cycles. There is cases where this can be slower than actual full compilation, but they are so rare, you have to specifically create the classes to be slower. And from my experience, I was hit by this kind of problem once, but it was a bug inside SBT, and it's already fixed. So don't worry. Do you got any question at this point?
So what happens if you don't explicitly declare the return type of a method and you rely on method signatures for hashing?
OK, so the question was, if I don't provide the type in my method, how I can overcome that, how I can work with that. The answer is simple. During the phases that were plugin, in the end of the compilation, compiler know all this stuff. So the type is inside the method. So there is symbols inside the compiler, and there is types, and all of those is present there. So I can just ask from the type of the method at any point. So I don't have to explicitly try to interfere it, because compiler has all this in place. OK. So the second part is name hashing. And name hashing is what is using right now, what SBT actually is using itself in the tips of the compilation. And this is basically improvement of the previous idea. So it's more sophisticated. And I want to explain as a difference to the previous algorithm. First, and the most important change, is the change of how we represent the API. Our new API is, except for, there is not a single hash. There is now multiple hashes. And each hash is stored for a given name. And what the name is? The name is, it represents the cumulated hash for all members I declared with given name. So if I have, in my class, have multiple overloaded methods with the same name, they're all hashed into the one thing. If I have case class and companion object with the same name, it is also hashed into the same hash. Of course, in the real world, it's much more complicated, because we have to treat differently the implicits. We have to treat differently the members, inheritance, and members, because it's not actually, if if my parent of my class, there is a new method introduced, I have to compile my method. No matter even if I'm not using that name in my method, because this member might be abstract, for example. So this is, again, a simplification. The second part that is changed is how we store the dependencies. Right now, for each file, for each compilation unit, we store not just the set of files that we depend on. We store the set of files and set of names that we depend on. And so it means that if given name is used in my code, so I call method apply, I call method foo, it depends on the name foo. If there is a class named foo in my code, I also depend on the name foo. If there is a typed or type parameters with given name, it all goes into the name dependencies. And as previously, we stored the file dependencies. I mean, which file we depend on. By files, I mean source files. And this was not shown because it was previously simple. I mean, if I depend on a given file and its API changed, I need to be recompiled. Right now, the isAffected method is slightly more complicated. Right now, except that I need to check if I depend actually on that file, I also need to check if its file was, if one of the names changed in that file is used in my context of my class. And this is like the core of this idea. So if I have methods, if I have class A with method foo and bar, and only the foo changed, and I have class B that used the bar, no matter from which class, which object. If just the foo changed, I'm sure that nothing is changed in my class, except only if I not depend of. It's not implicit, but this is details right now. So, can we do better? Can we somehow, because this is like really simple, really trivial idea, and this is heuristic, so probably we might be able to produce like complete graph of dependencies, like as small as possible, that we are sure that this and this and this need to be recompiled if this place changed, this method, this class. Probably we can do that like to be like fully precise, but this is really hard for Scala because Scala is a complicated language. So, but can we do at least a little bit better there? There is work on that. It is this pull request from Grzegorz Kosakowski to Zinc, actually. It's aimed into the SBT 1.0, if I recall correctly. And this is all about the small granulation. And right now, we have this. If I have file with multiple case classes inside, if I change the type signature of one of those case classes that is used in one place somewhere else, it means that I changed apply method, and it means that hash for apply is changed for that file. And if all of other case classes is used in almost all classes in my code base, it means I have to recompile them. Because right now I'm storing the name changed in the context of whole file, not the class. And this pull request changed that. I mean, it splits these dependencies into the level of the name in class in file, not just name in file. So it should like make this graph about the dependencies smaller. So probably the compiler will run better. And by run better, it means it will compile less classes for given change. Another level that we can improve our compilation is we can lose some precision. Because SBT, it's aiming for 100% of precision. It means if incremental compilation complete fine, it means the full compilation will never break. This is an idea. There is some problems with that, of course, but it's like a small one. Or it means that if I change something, I want to be sure that all of required class to be recompiled is actually recompiled. But if we can loosen this, so for example, okay, I can say, let's get like 90% guarantee that it's correct. So in the end, you have to compile it again, like do the full compilation to be like 100% sure. We can be much faster. And this is actually what IntelliJ is using. They don't care about multiple edge cases in Scala. Like, I don't know, the good example is macro, changes in macros. Because if the body of the macros changed, it means that there is like no guarantee, taking from the change of that macros, that the output of that macro will be the same. So each usage of that macro need to be recompiled. And there is more about implicits, about member reference, and complicated types in Scala. So that is why IntelliJ is sometimes my complete fine, but then I break. So there is a field to speed this up. And of course, you can speed up your incremental compilation a little bit with few simple steps. And this applies for any incremental compilation. First idea, provides return types. And I don't want to speed up the Scala compilation because I don't know if this speeds up a Scala compilation in the end. I don't see like any actual numbers for that, but it should speed up at least a little bit incremental compilation. I mean, less files will be recompiled. Why? This is an example. If you play around collection, for example, so in the end, both implementation of teams, has pretty much the same API in the end. So you can map on this, flat map, and stuff like that. But if you change the implementation from the top to the bottom one, the type slightly changed. And for all tooling, it means I have to recompile it again, because tooling is not that smart that can, OK, it was iterable, but I was using only the map and flat map, so I don't have to recompile everything. It will recompile everything. But if we provide the type there, we are safe. We are safe on that. And the second thing that you can do, just don't use multiple classes in one file if you don't need to. If there is like no sealed class, if there is of course case class and class and companion object, you have to store in one file, but not more, because there is one big limitation there for each compiler. Scala C cannot compile the half of the file or just class from the file. It needs to compile whole source, which means if there is one case class at the top just changed, you have to compile all the rest of the file. It means, and sometimes it means like really hard computation, especially if you have macros or complicated types there. OK, so do you got any questions? I don't. OK, so thank you.
If not, thank you very much, Krzysztof Romanowski.